good. So the second part, here we go. Generalizing axis swapping into observable swapping. I'm curious, now that I know more about observables, maybe that's going to help. There's some fancy animations in here. Maybe that's going to help me understand exactly what this is all about. But you have to keep in mind that what I'm trying to understand is a bit more the swap operation and how can you intuitively understand it within the quantum Fourier transform algorithm. Because, as I said, it basically it's like it's kind of intuitive on the one side when we take a look at the circuit that starts with the swaps, but it's not so intuitive on the inverse of the circuit, which again, maybe I'm just like banging my head against like a useless problem. Whereas like you can just approach intuitively as a compute and uncompute, but still it does have some. If you think about the inverse circuit where the swaps are at the end, there is indeed some kind of reasoning why would you want to use that circuit. It has sort of a standalone meaning to it, which is the sort of the rotations and all that kind of stuff, being clockwise, counterclockwise, etc. So I just wanted to basically try to see if there's any intuitive understanding of the swap in there, the swap operation in there. And I was just plain curious about whether there's a way you can define a swap from an interference perspective that is leading to some kind of interesting insights, right? Because if you remember well, when I did the Grover, breaking down the Grover algorithm, the second iteration, I kind of realized that if you define the phase as in like adding, I'm still lacking the vocabulary, but like adding some more component, like if you've got, like, for example, these are your states, right? And 1, 1. So, and then I think it was something like, at that point you're having basically that part was phased out by 180 degrees, and the way to get there was by taking simply the original one and then kind of conceptually adding, I don't know, twice that, right? So those things kind of cancel out, and then you end up with this element in here. If you're doing it this way, then you could see how the axis flipping that Craig defines was actually working. It was giving a fresh perspective to Grover's algorithm and how the actual amplification effects play into this whole thing, because you're basically flipping all that and then you're turning the original plus into a minus, and so suddenly these two components, instead of having a cancellation, a destructive effect, they have like a constructive effect, which is like 3x, right? And so you're amplifying that. And that might be not the correct way to see it, but it just, I don't know, for me, it's a bit more intuitive than talking about the inverse about the average or the inverse about the mean and all this kind of stuff, which is just maybe a mathematical proof of correctness, but I haven't seen sort of a more intuitive breakdown than that. So let's see. Maybe the swap, there's some kind of, because at the end of the day, when you have a swap, right? Like imagine you've got a superposition that is basically 0, 0, the same 0, 1, 1, 0, 1, 1, and you've got maybe that little element, that one element here phased out, and then you're having the result of the swap, right, is you stay with plus 0, 0. You basically stay now with plus 1, 0 and minus 0, 1, and then plus 1, 1. So you've kind of, you could think of this swap as you've moved you can see it as you've moved the phase around. So taking a look at the things that change here, you could think of, these being as sort of in the middle. You're kind of conceptually doing these. Are you doing these kind of, because this cancels out, like, is it like, cause then these would cancel out with these, but you still need to have another one, so you actually need to have that twice, and then you need to have that twice. So you're kind of, you can think of it conceptually adding this piece into the superposition. I don't know if that has any. That's for the particular case of a superposition, because if you think about, like, you're just having a non-superposed state where it's just, what is like, maybe it's because if you just got, like, I don't know, like these, right, and then you're swapping these two, then you're gonna got these, but that doesn't have any. I mean, you could break it down the same way, right? But it's useful for that particular case because this is what we want to take a look at. So we're going to take a look at the quantum Fourier transform that has the circuit that has the slopes at the end. I'm hesitant to call it the inverse, the non-inverse, because it's just confusing already at that point. But that is interesting because you've got phases in play, and actually that's important because all what you're doing with the QFT is you're encoding a wave in the phase. So that might have an intuitive interpretation. So it might have an intuitive help. It might be a sort of intuitive help to understand why is the swap needed. So this is what I'm trying to understand. So let's go back to the actual original goal of the video. Let's go through the rest of the blog article, and then let's see if that brings any insights into these. But it's not a. So, but that would, let's deep dive into this in the next video, because I think that definitely can be an interesting way of seeing it. Because my point here is that if you have so you've kind of folded things up with the QFT, but then so you folded things up. Yeah, but that's kind of your end result. So you end up with a result, and then you want to kind of add this partner interference to basically swap it. I don't know. I don't think it's going to help. I don't think it's going to help because that's. Because yeah, that's the whole point. The whole point here is you start with a. Okay, let me go through this first. I'll go back to this in the next video. So generalizing, it was a bit of a tangent, but generalizing axis swapping into observer swapping. What happens if we apply axis swapping but don't use the same axis for each qubit? For example, suppose that we use the x and the z axis on qubit 1, but use the z and the y axis on the qubit 2. That is to say, we apply these and these, then these. What happens? What happens is that the two qubits get swapped, but they also get rotated. If the first qubit had a state pointing along the z-axis, then once the state arrives on the second qubit, it will be pointing along the z-axis. Correspondingly, a z state on the second qubit will become an x state on the first qubit. Instead of swapping x1 for x2, we're swapping x2 for x1 for z2. Also, we're swapping z1 for y2. This suggests a way to define a more general swap operation. Given two pairs of observables, A1, A2, and B1, B2, if each pair anticommutes, and is independent of the other pair, their commutator satisfies these, and so then you can swap this is an operation that exchanges states along A1 for states along B1. What the hell does this even mean? And states along A2 for states along B2. The amazing thing about this generalized definition is that it works for any observables. We can apply to qubit access, but we can also apply to complicated multi-qubit properties. As long as A1, A2, B1, and B2 satisfy the correct commutation and decommutation relationships, it will work. To demonstrate what that means, let's do an example. That's what I like. For A1 and A2, we will use the Z and X axis for qubit 1, but for B1 and B2, we'll use observables involving many qubits. B1 we will use observables involving many qubits. Specifically, B1 will be the z-axis parity. The z-axis parity of qubits. Okay, so now we're getting it. Okay, so let me just. So we're really talking about observables. This means things that you want to observe. So literally, kind of, because the parity is also an observable, right? So something you can measure. You measure this observable by preparing a target qubit in the 0 state, C-naughting each of the qubits into the target and measuring the target. So will be defined as the parity of several. So B2 will be defined as the parity of several qubits, but it will be an x-axis parity, and it will not use the same set of qubits. B2 will be the x-axis parity of qubits. If you know how you should check that the observables A1 equals Z1 and A2 equals X1 and B1 equals and B2 equals have the correct commutation and anti-commutation relationships. Based on that being correct, we can implement the swap of. Okay, so oh my god, let me wrap my head around this. So basically, you're swapping observables. So you're swapping things you can measure. It's like you want to say, I don't know, I want to swap energy and position. I don't know. So you're swapping results of operations and measurements, right? So you're kind of swapping So you're not just swapping qubit states, but you're swapping more complex operations on qubit states. So what this is saying is the observable blah blah blah. So what was the example here? For A1 and A2, we'll use Z and X axis of qubit 1. So you're saying that especially B1 with the Z-axis parity and B2 defined as the parity of several qubits, but so the X-axis parity. So you're gonna flip the parity and the Z and the X-axis. Okay. If you know how, okay, so we can swap with big observe. So we can check that it's actually working by moving a qubit into the big parity observables, then retrieving it. This should work even if we put all kinds of junk into the qubits used to define the parities. Here's what that looks like when simulated in Quark. So wait a second. So what have we got here? The swap operation, then it's like this. So you're not. So the thing here is, instead of just having the y, you're having like. Wait a second. That's confusing. Where I'm a bit lost. So Z and X axis. So that's kind of the definition here. A1, B2, A2, B1, A1, B2. So these, okay, because this follows that pattern, right? So you do like, it's like the XOR pattern that you've got like the controlled, and then the controlled. So that's kind of the same. No, but it's not the same really. I mean, okay, it's similar in like that there are 3 steps and that the third step and the first step are the same. That's what you've got here. And I guess the one in the middle doesn't really matter where the control is. No, it should matter in this case. So you can so for example A1 and A2, Z and X axis. So this is A1 and this is A2. That's why it's the X axis. That's why it's using an X axis control. So this is an X axis control and that's kind of A2. And these are both Z axis controls. So this is the Z in here. So this is kind of both A1. And then here you've got the party observables. So he's saying is that, what Kirk is saying is that to calculate the party, of qubits 2, 3, and 4, qubits 2, 3, 4, and 5. So this is the party. And so this here, I'm using another color. This here, a target qubit into the 0 state, C0ing each of the qubits into the target, then measuring the target. B2, okay, an x-axis party. What is the same qubit? But we'll not use the same set of qubits. But are these, okay, so 2, sorry, that's not correct. This is for these, and then these guys in here as these. And so, okay. And this is calculating the parity. And here the reason this is built this way is because it's the same as doing a Hadamard and then the C0 with the it's like going to, you know, doing a Hadamard sandwich, because it's the parity. So it will be the same, but you're doing a Hadamard sandwich. So basically, Craig is using his axis control notation, or yeah, which is more compact, because you would need to do the Hadamard sandwich to calculate the parity on the z-axis, because you know, you cannot, like, the control not way to do that is the way you do it in the x-axis. Okay. I don't know if that particular example has been chosen just because it works, in the sense that he says if you know how, you should check that the observables have the correct commutation, and I don't know how, so I'm not going to check it right now. Let's see. But basically, that's how you map everything that's explained in here with these. So here you do a Hadamard sandwich, and then you would do the same you're doing with the other two operations. But you can summarize it like that. So if you don't know why, then check out the axis control. Check out, that's the so no, not here. So cert.com. So you basically have the operations as controls, and that's a really, that you must read that. Like, definitely read that. That's a really insightful one. As it's a bit of a, so here we've got the QFT actually. There's also hammer sandwiches. Maybe it's something to take a look at as well. Okay, so this is this, and then let me clean that up. And then you've got that animation here. We can check that it's actually working by moving a qubit into the big party observables. Then retrieving it. This should work even if we put all kinds of junk into the qubits used to define the parties. Here's what it looks like when simulated in Quark. So you're doing the swap in here. So you're technically what does this mean? So why is this done twice? We can check that this is actually working by moving a qubit into the big party observables. I mean, again, what are you kind of swapping here? It's a bit abstract in terms of how can you check that. This should work even if we pulled all kinds of junk into the qubits used to define the parties. Here's what that looks like when simulated in Quark. So we've got here the parities. But what does notice how the blocks here display at the bottom right matches the display at the top left, and it rotates around. Yeah, this one and this one, this one and this one. That's because the qubit state from the top is being swapped into the middle and then into the bottom. Okay, so that qubit state is kind of swapped in here, and then in here. It's weird though. Can I pause the animation? See, it's sort of. That's even though the middle we passed it through is going kind of nuts. Yeah, actually, if you look closely, you can see at the end that we left some holes behind in the middle. What holes? Actually, if you look closely, you can see at the end that we left some holes behind in the middle. It's pretty neat. We start with a single simple qubit, then moved its value into some big complicated observables amongst a bunch of junk. Then managed to retrieve the actual value. This demonstrates a very important lesson. Any pair of anti-commuting observables can store a qubit. That's weird. This fact is key to understanding many error-correcting codes. Interesting. Which spread a single logical qubit over many physical qubits. And we can use this definition of our generalized swap operation to move qubits into, between, and out of these big complicated anti-commuting observables. Whoa, I think we've generalized enough for one day. Let's look at a totally different approach to swapping, XYZ swapping. Okay, that's a totally different approach. Interesting. That's pretty abstract, but I think I get what basically Craig is saying, that you can swap like a qubit, but then this means so you're literally, but that's pretty nuts. So you're saying you're literally encoding one qubit into these qubits in here, and you're actually encoding those parties into one qubit. Does this mean this as well? So you're encoding those parties into one qubit in a way that you can actually retrieve that back if you know how it's been encoded, but that's pretty nuts. How do you even calculate, like, how do you even know? So you're encoding parities into one qubit? Wow, I don't know. That's probably going to be the title of the video. So swapping can be generalized into an actual super interesting way of encoding things. That's pretty crazy. That's totally not. It's totally not intuitive. Okay, so swapping is not, it's not just, flipping the cables in this case. This is a pretty nuts generalization. Wow. I'm trying to still wrap my head around this, but it's quite. So you could technically do that, and then you've got all that information encoded into one qubit. Crazy. Let me clean that up. Let's move forward. XYZ swapping. So it is a fact that any two qubit operation can be decomposed into local single qubit parts and one non-local operation of the form. It is a fact that any two qubit operation can be decomposed into local single qubit parts and one non-local operation of the form. These, I don't know what it means. Equivalently, we can split the non-local part of the operation into three commuting parts: an x-party phasing, an x-party phasing part, and a y-party phasing part, and a z-party phasing part. The size of the numbers x, y, and z gives a measure of how non-local an operation is. For the swap operation, the non-local parameters are x equals y equals z halves. Interestingly, this is the most non-local an operation can get. If we follow up the swap with another operation, the size of the parameters can only get smaller. That's because, for example, once z goes past the halfway mark, it starts getting closer to the operation, which is local. Anytime our parameters leave the -1/2 and half range, we can make their magnitude smaller by applying +/-1 offset of them. What did I just read? If we want to perform a swap based on the non-local decomposition, we need to know how to implement operations like Z1, Z2, Z. What the operation does is leave the 0, 0 and the 1, 1 states alone, but phases the amplitudes of the 0, 1 and the 1, 0 states by -1 to the power of Z. Okay. When the two qubits agree on the Z value, nothing happens. When they disagree, that part of the superposition gets phased, and is the agreement versus disagreement of the two qubits. Their parity that controls the phasing. That is why I call it Z-party phasing operation. What? By creating analogous circuits for the XX and the YY interactions and chaining all the three-axis parity effects together, we get a swapping circuit that at least looks qualitatively different from XOR swapping. Wow. What? The X, Y, and Z parts can be placed in any order. As long as the single qubit gates are adjacent to the two qubit gate with the corresponding axis, it'll work. Note that the XYZ construction above is correct up to global phase. The RHS of the above diagram has an additional global phase factor of I. If you want to apply a control swap, this causes phase kickback that has to be corrected with an S inverse gate on the control. There's a lot going on here. What the? I haven't even fully digested the observable swapping, and that's already going into an even crazier direction. Gotta slow down a little bit, I think. By creating analogous circuits for the X and the Y, okay. That's correct. Okay, this I have no idea what I'm reading here. Specializing the XYZ swap. Consider that the Z-axis instructions commute with the Z parity part of the construction passes through Z part of the XYZ swap. This means that the thing that moves the Z-axis interaction from one wire to the other must be just the XY part. So if we happen to be in a situation where we only have the XY part of an XYZ swap, it's still possible to move Z-axis operations across. Z-axis interactions will move to the other wire when the Z part of an XYZ swap is missing. However, moving an X-axis interaction across the swap with only its XY part doesn't work. For that to work, we need a Y part and the Z part. The X part doesn't matter to X-axis interactions. In other words, as far as moving operations is concerned, we can specialize the XYZ swap to a specific axis by dropping the part of the XYZ swap axis corresponding to that axis. Yeah. There's another interesting specialization that occurs when we drop even more of the swap. If we drop one of the axis interactions and then drop all of the single qubit gates, we end up with an operation like Z1. The interesting thing about this circuit is that an x-axis interaction on one wire after the circuit is equivalent to a z-axis interaction on the other wire before the circuit. But the same is not true in reverse. But when you go from right to left, complicated stuff happens instead. This one-way okay phenomenon is analogous to the fact that removing the first C node of an XOR swap will cause the swap to only work properly in one direction. But now I'm in danger of retreating information on XOR swapping, so I'll leave figuring out how the two relate as an exercise for the reader and move on. Danger of retreating information on XOR swapping, so I'll leave, okay. To relay. Far swap. What if the two qubits you want to swap are next to each other? Well, if there's a path of connected qubits between them, then you can swap one towards the other until they are adjacent to the important swap, then return to the starting position. Break the swap chain down into C nodes and you get these. Yeah, that kind of makes sense. You're swapping these. You want to swap those two qubits, so you're kind of doing all the chain, and then you're undoing it. The above construction is not very efficient. It has depth 6d plus 0.1, where d is the distance between the two qubits. So we can do much better than that. We can cut by a factor of 2 by meeting in the middle. That's interesting. And a factor of 3 by pipelining the intermediate XOR swaps in a clever way. The result is a distance d swap. That's pretty interesting. What is going on here? What is going on here? Distance d swap with depth d plus 0.1. So it looks like you're kind of intertwining these halves kind of brought together, and then these two halves kind of brought together, and then you get this kind of mix max in here. This X. But still, that's confusing in the sense that So here you've got the an actual swap, but then in between here you've got, so these three operations belong to one swap, right? But at the same time, you've got another swap kind of here in between. So that would be one interesting thing to analyze more carefully. The fact that you can kind of merge two swaps like that. You can really do that. Wouldn't this be the same as just doing it separately? Like, do they have to crisscross like that? That's something to check. And okay, and that we're reaching the end so much better, although we're still assuming there's a path between the qubits. What if there's not the case? So we've got, okay, with quantum teleportation, gradual stack, unless we have some sort of shared entanglement. If you have some mechanism for building up entanglement in your two disconnected components, then you can use that entanglement to sort the qubits with quantum teleportation. I mean, I guess the idea, I guess what's going on here is your quantum teleportation, but you're adding a swap to it. So you're basically, okay, so you're ahead of time. So I guess what's going on here is that you're twisting the entanglement before the actual teleportation happens. Yeah. And so when you will execute the teleportation protocol, and then you'll figure out whether you need to do like a control node or control set based on the measurement results, then you'll kind of get the flipped result, because at the end, okay, let me open quickly Quirk. So if you open quantum teleportation, right, you create entanglement this way before you do the whole thing in here. So, and basically the whole actual teleportation. No, okay. So that's basically like a twist. It's like an entangled teleportation, really. It's teleportation in both ways. Okay, so I get it. So this is not, that's not what I meant. So this is one thing, this is the other one. So it's A and B, right? Like Alice and Bob. And then you're just doing, I mean, you could as well do it in two steps, right? But that's kind of doing it all in one step. Because this is then one of the entanglement pairs, and this is then the other one. So it's not that you're using the same circuits, you're using two separate circuits kind of blended into one here. Okay, cool. So I think that doesn't need to be checked farther. There's more than one way to break down the swap. True, any pair of anti-commuting observables can store qubit information. That is pretty fancy. You can use observable swapping to store retrieve that information. That is actually a really good insight. When you remove pieces of a swap, some access instructions may still switch wires when moving across the swap. That's something still to explore. And even qubits isolated native machines can be swapped if you can build quantum entanglement between the locations. Yeah, there's a lot. There's a lot to say. So I wanted to check these here quickly as well. So if I clear the circuit, if I do, so if we've got the block sphere here and the block sphere here, right, and then we're doing the thing here, and so you're basically that's your swap, okay. And so what I wanted to prove is that, so but then you can now do, so you could technically do this, right? And do another block sphere here, so you're kind of the this is kind of chaining through all that. And so what Craig is doing here is like you don't have to do them sort of inline, like this is one swap and this is another swap, but you can actually sort of intertwine those operations, and that still works, which is basically what you've got here as a pattern for this X, right? But my point is, I think that's not something specific here that matters. It's just it's just maybe more elegant, but you could as well do it in it's in a serial way, and then you still don't increase the distance or the amount of operations you need to do, right? But it's an interesting way to see you can actually connect things down that much. So if I get this away and then I say move this here and this here, move this here and this here, so that still works. So, but that works with any kind of permutation, with any kind of combination, right? No, 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 no. Look at this. This doesn't work if you do it like that. That's interesting. Why? This also doesn't... Okay, this works for 0 and 1. Huh. It works for 0 and 1, but it doesn't work for anything else. And if I do it this way, it works for 0 and 1. It works for plus and minus, but it doesn't... Now it works. This works for everything. Okay, interesting. That might have to do with what Craig is talking about here. So that you can drop one of the operations and this will still work one way. Okay, so but this is then material for another video. So I'm gonna deep dive into X. So these, I think I can close that. So that's really interesting in terms of encoding. It's definitely helpful for. It's you don't say many error correcting codes. That's interesting. It's for me, it's pretty mind blowing that you can encode like something like an observable into a qubit, because that's really what this is implying, right? You can encode a qubit into an observable, but you're also swapping the observable into the qubit, right? That's pretty nuts. The fact that one single qubit can hold that type of information, you can then retrieve it. But that's because of the entanglement. That's definitely because of the entanglement. That's pretty crazy. Okay, but this X, Y, Z swapping, this is something that I haven't really understood. And I think it has to do a little bit with why this construction is possible, and it's not always possible in all the different configurations. Interesting. So why can you kind of like merge the operations and it still works? This is something that I want to kind of break down a little bit more. But let's do another video on sort of deep diving into XYZ swapping. There's definitely something interesting here in terms of the party phasing, this party phasing concept. Yeah, this is way bigger. Like it's become a way bigger tangent than I expected. I don't know if this is gonna help me understand the quantum Fourier transform, not this one, but the one that has the swaps at the end. But that's interesting. I'm just trying to think a little bit about it, but it's pretty it's pretty crazy, man. I mean, if I go to bookmarks and Let's check in QFT. I think this is this. So why? Like if I put these amplitudes in here, right? And now we're swapping. So what is the intuitive meaning of this swapping, right? And here, but it's the wrong way of seeing this. Here, you don't want to have that. You want to have like an actual wave that's in like whatever superposition, right? And so this tells you, let's say we're gonna have plus, plus, minus, plus, right? So this is the superposition you have and so it's like how can you basically do that? It's like what's the seed of that? Can you get to that superposition? How can you get to that superposition by means of rotating things? So what this is telling you is like that's what you need. But look at this. So basically maybe that's what this is doing is just flipping that whole thing like these. Kind of that's the point that stays, and then it rotates this way and that way. No, what am I? No. This one goes up, this one goes down, and this one goes down. What is an intuitive definition of these, and why is this needed in this case? Maybe you should try to rephrase what this version of the QFT is trying to do here, right? Which is trying to basically, you've got a superposition, so it's in kind of the most generic way is given that superposition, what other superposition, given that equally distributed superposition? Because pay attention, that's the point here. It's an equal. The amplitudes are all equal. It's just the phases that are changing. So what set of or what kind of state? What kind of state you need to use, or you can use to actually, or a wave that's encoded in the phases in here. What are the That's really what what are the amplitudes? No, what are the frequencies that make up that, right? And this is the answer. Is these, not these. These. But then why, what's the intuition in here? Is this because my current feeling is these is really a correcting mechanism. But if you're correcting something, is because you can't do it otherwise, right? So, but why can't you do it otherwise here? Why is it that you only have that particular way of wrapping things up? So you've got Hadamard operations, you've got like rotation operations and controlled rotations. So maybe this is what I should dig into. Maybe I'll do another video session on these first, so to try to deep dive into these, talk about interference in here, as I said, and then maybe the next videos are gonna go back to that part here, the XYZ swapping. Although I don't know which one I'll do first. Maybe I'll do this one first and then the other one. I'll kind of think a little bit through some ideas. Because this is kind of what I'm missing for the QFT. I'm trying to understand really sort of intuitively. I understand how the algorithm works, but I'm missing the piece of like why the swap in here, in that particular circuit. So, yeah. Cool. Stay tuned for more.